everybody for being here. Today we have Elias, Adediran. Sorry if I...
It's okay.
One of the best dressed speaker out here. So a brief introduction about him. Elias Adediran is a doctoral researcher in ocean engineering at the University of New Hampshire Center for Coastal and Ocean Mapping, Joint Hydrographic Center, where his research focuses on improving digital bathymetric models by characterizing interpolation uncertainties. He holds a master's degree in ocean engineering, ocean mapping, and graduate certificates in ocean mapping and geospatial science from UNH. Before that, he earned a first-class Bachelor of Science in Surveying and Geoinformatics from the University of Lagos and a national diploma with distinction from Yaba College of Technology, Nigeria.
Thank you so much for the introduction. Thank you, everyone, for joining, both in person and online. Today, I'll be talking about why it is not just depth and why estimating uncertainty in interpolated bathymetry is important and critical, and some of our ongoing efforts in trying to do this reliably. I know we have a bunch of maybe non-ocean mapping students or like experts. We have expert ocean mappers here in the world, but I know that we have some people that are kind of ocean engineering background, and that's why I'm going to start this talk with this question: that how many percent of the world's ocean do you think is mapped to modern standards? So can anyone that is maybe not none of the GEPCO scholars, and of course, we have the experts in the world here. The question is not for them, but maybe from people from ocean engineering, can anyone give it a try? Pick up, don't be shy. Yeah, go ahead.
I'm gonna totally embarrass myself, but 20%.
Oh yeah, that's a good one. That's close. It's currently 28.7%, and when we look at that's the global ocean. When we look at the United States waters, in the interest of time, I'm just going to tell us that's 56%. And what is this telling us is that a large portion of the world's ocean is unmapped or unsampled. And as a result of this, we typically require interpolation to fill these gaps, amongst these sparse bathymetric data sets that we have. So we go from what is on the left to what we have on the right to a continuous model of the seafloor, which is very important for numerous scientific and commercial applications. After this, I want to show us some of the example of data sets for creating digital bathymetric models based on coverage. Of course, we have complete bathymetric data set for multibeam echo sounder, single beam echo sounder. But maybe the one that interests us most today is the non-incomplete bathymetric data set, which could be from setline spacing surveys, that could be from multibeam echo sounder, single beam echo sounder, or skunk-striping, which is a combination of single beam and side scan sonar data set. And of course, we have archived data sets too, which are also incomplete. And it is this setline spacing surveys data set and the archive data set that actually requires us to fill the gaps with an interpolation method. But of course, this interpolation method introduces some inherent uncertainty into the digital bathymetric models. Just to give you a closer view, or maybe a better appreciation of what I mean by bathymetric coverage, if you look at this very beautiful digital bathymetric model from the Gulf of America, it's very beautiful. But if we try to look at what are the data sets that were used to create this digital bathymetric model, this is what that looks like. And you can see the cyan color there, it's the measured bathymetry, and the interpolated one is the interpolated region is the red. Again, maybe let's zoom more into it to have a better appreciation of how much of interpolation that we are doing. So again, I think I don't need to describe this. It's kind of there we can all see it. But the question is, what about the uncertainty introduced by this interpolation process? And as we know, with any scientific measurement, the uncertainty that comes with this digital bathymetric model is important. like for numerous scientific applications. I'll get to some of the applications soon. So I like to think about this like with the going away tool of hydrography with like, with 3 legs. How deep is it in terms of depth? How well do we know it in terms of quality, uncertainty, or like coverage, and do we have features detection? Then, of course, who provided the data? Like, who do we blame when something goes wrong? And if this part is missing, which is the quality of the bathymetry, you see the like the stewed kind of like tipping off. That's not good for us. So what I'm saying is, bathymetry must carry appropriate and accurate quality metrics. And these quality metrics are being defined by IHO, International Hydrographic Organization, and of course, NOAA also has their own equivalent quality metric frameworks that they use. So the question is, who cares about even this interpolation uncertainty, and why is it important? A lot of stakeholders here, because digital bathymetric model is very important for widespread use. Is being used a lot, for different kind of application. The mariners care for safety of navigation and to avoid maritime accidents. Environmental scientists also care because they need accurate bathymetry to study benthic habitats. Coastal engineers and planners also care because they rely on accurate bathymetry to design resilient coastal infrastructure. Government agencies like NOAA, they use uncertainty information to guide where to collect data sets, and of course, to support products like the National Bathymetry. Insurance company, they probably care the most because money is involved. Because uncertainty translates into financial risk exposure, so they probably care the most. And hydrographic companies or survey planners also care because they need uncertainty information to optimize their survey design, trying to balance cost, time, and the required data quality, trying to meet specification. And of course, the list goes on. So why methods for quantifying the uncertainty in depth measurement are well researched and developed? We have what experts here that have worked on this. Quantifying interpolation uncertainty in digital bathymetric models remains a long-standing challenge. But does that mean that these are not, maybe some effort have not been made on trying to solve this problem? No, that's not what I'm saying. There have been some efforts, from way back. There was this paper by Jacobson, Calder, and Meyer. And we have 2 of them here. We have Brian here, and we also have Larry here, where they try to use Monte Carlo simulation to estimate the random error in some bathymetric compilations. But the limitation of the work then was that the approach was largely heuristic, and the error propagation wasn't data driven, and that was because of the nature of the data set they were using. In 2006, Brian also extended this approach by combining lowest interpolator like Quiggin and also Monte Carlo simulation to try to estimate the uncertainty. But maybe the limitation of this approach then was the method wasn't able to capture the spatial aliasing that was found in the data set, or even though it tried to compensate, it compensated for that using a global uncertainty inflator factor, but that kind of also limited the use of the data set, because you can't really determine where the aliasing is happening, and you just kind of introduce the inflator factor all over where, so that kind of limited that the approach. Hopefully, I translated your work, Brian. I'm trying to be careful, but I think that's my interpretation of what I read in your paper. And in 2012, Elmore et al. Also further tried to extend the Monte Carlo simulation approach by using a Bayesian network approach. But the biggest limitation of this was the uncertainty that they estimated was even more than the uncertainty that the Monte Carlo approach was giving. So that was kind of like limitation of this. Because of time, I don't want to really go into the details. And more recently, which is part of my master's work, we looked at this using machine learning approach by trying to use predictors such as distance to nearest measurement, slope, and roughness of the seafloor to estimate interpolation uncertainty. But what we found was that while these predictors, slope, roughness, and distance to measurement, they were important predictor of interpolation uncertainty. They were just able to estimate about 50% of the variability in interpolation bathymetry. And we learned, from this that the way we were defining the slope and roughness kind of limited the spatial the spatial scale of our analysis. So kind of learning from all of this based on the previous work that has been done and what I also did during my master's. So our ongoing effort now is trying to develop an algorithm for doing the same work, like quantifying interpolation uncertainty. And what we are trying to do, the algorithm that we're kind of developing is called iBLUE, which is Interpolated Bathymetry Linear Uncertainty Estimator. And what is iBLUE really trying to, what question is iBLUE really trying to answer? The question is, how effectively can spectral and spatial statistical methods be used to quantify interpolation uncertainty in systematically sampled bathymetric surveys? And I think there is a key word here that maybe I should kind of highlight, which is the systematically sampled. What I mean by that is as surveyors, we just don't go out there to survey randomly. Surveys has to be systematic. And an example of a systematic survey is setline survey, setline spacing surveys. Also this could be also be skunk-striping, just like I mentioned before. You can see that's the combination of bathymetry and side scan sonar data. The white that you see in the background there, that's the side scan sonar data set. And of course, even sparse data sets too, as far as they capture the seafloor morphology well enough, and it's not random. You can see there are some pattern in the data set, so it's not random. So that's what I mean by the by systematically sampled bathymetric surveys. So what is iBLUE really doing? The first thing is that it models interpolation error as a stochastic process, just like others have also done in their papers. It's characterizing interpolation uncertainty using nearby observations. It's assuming that the seafloor statistical properties are locally consistent over short spatial scales, which is consistent with Tobler's first law of geography, which states that everything is related to everything else, but near things are more related than distant things. Then the other assumption that we are making with iBLUE is the seafloor statistics exhibit local second order stationarity and limited directional dependence. So based on these assumptions, we are using, then we kind of then use spectral and spatial statistical method for estimating interpolation uncertainty. I'll kind of take some time to go into what the details of the spectral and the spatial statistical methods, because when I mean spatial statistical method here, it's not the classical Quigging that we all know, we think of this is different and kind of new. So let's look at the spectral approach, which it's the spectral estimator, which is trying to estimate interpolation uncertainty in the frequency space, not in the spatial domain. And just with spectral analysis, we decompose the spatial signal, which is bathymetry in this case, into a frequency component, and from there, we can estimate what our power spectral density is. And power spectral density, in essence, is the variance distributed across spatial frequencies. So in this context, power spectral density represents the contribution of the different spatial scales that are contributing to seafloor variability. And we know that interpolation uncertainty arises from the unresolved variability, we have, amongst the data set. So if we want to try to capture the interpolation uncertainty, then we can the power spectral density is integrated across like these spatial frequencies, and it's weighted by a spatial kernel to estimate how variability propagates over the interpolation distance. And the resulting quantity is a scale-dependent estimate of the expected interpolation uncertainty. So to kind of like give you an intuitive feel for what is going on with the spectral estimator, especially like people, I know like we have people that are more mathematically inclined here. So we take the sampled seafloor, and we try to preprocess that using the normal, the standard preprocessing steps in spectral analysis, which is the trending and applying windowing function. Thanks to Tom Lippmann, for your class. So we do that. We preprocess the sampled seafloor, and we use fast Fourier transform to decompose the sampled seafloor, which has been detrended now. And from the Fourier transfer, from the Fourier coefficient, we can calculate, we can estimate our power spectral density. And we then define a spatial kernel which as a function of distance. So combining the power spectral density and the spatial kernel, we can get like the variance. And once we take the square root of that variance, we can get like what the uncertainty is. So that's really the idea. Like we are using to that's how we are estimating the uncertainty in the frequency space, like kind of like using the spectral estimator. The next, go for it. I think he was trying to take the picture before I took. Yeah, so the next method, which is the spatial statistical estimator, like I said, this is not like again. What this is doing is it's estimating the uncertainty in spatial domain using sliding windows, as you can see, kind of like from like the sampled seafloor to kind of like having some sliding window that kind of like try to represent with those brackets, and the window size is tied to the interpolation gap distance in order to ensure scale consistency. So within each window, and this is really where the stats that we are doing becomes important. Like, so the way we are computing the local seafloor variability is by using range statistic. That is taking the maximum value in the window and subtracting it from the minimum value in the window. So that's how we are estimating the local seafloor variability. And the next step is across all the windows, then the distribution of the range values is then summarized using like average or mean. So that's where because I want you to pay attention here. You'll be seeing spatial average range a lot as we go forward. Is this presentation? So what that is doing is it's just taking the mean of the distribution of the range values. The second spatial statistical estimator is the spatial envelope range, which is not just taking the mean now, but adding 1 times the standard deviation of the range values. So this which is the spatial average range, it's designed towards flat seafloor, and maybe the cell, which is the spatial envelope range, is designed for more complex seafloor. So kind of like putting all this framework together, because I've said spectral estimator, spatial estimator, kind of like putting everything together. So the spectral estimator is the power spectral density, like iBLUE. The spatial statistical estimator is the SAR iBLUE and the SAR iBLUE. So that's the methods that we've come up with to estimate our uncertainty. And how do we test this, or how do we evaluate these estimators? So we've done in this presentation, I'll just be looking at 2 test beds, which one is a relatively flat test bed located in the Gulf of America, and it ranges from depth of about 25 to 50 meters. The second test bed is a relatively complex seabed, which is located in the Gulf of Maine, and it ranges from depth of about 10 meters to 100 meters. And kind of like choosing a relatively flat and a relatively complex seabed, it will help us to really assess the performance of iBLUE, like, how those estimators are doing, like, when they are being exposed to different kind of seabed. To kind of like give you now, because we've kind of like talked about the spectral estimator and the spatial statistical estimator. So the way we are going to use them is, first is that we find a complete complete coverage multibeam echo sounder data set, just like I showed you now. So we try to simulate setline spacing survey by using some line spacing. And where we've selected the line spacing is, it ranges from 2 to 6 times the average depth in the area. So once we select the main lines, the remaining data set becomes the validation data set that we use to check how the estimators are doing. So from selecting the main lines, of course, the next step is to interpolate the mainline data set so that we can we make the surface a continuous surface, and we can compare that surface to the original surface. I want to point out here that the interpolation method that is being used is linear. That does not mean that we cannot use other interpolation methods. The reason why we are using linear here is because it's deterministic, it's computationally efficient, and it also helps to keep the local seafloor statistics stationary, so it does not introduce different kind of noise into data set. But that does not mean that we cannot use other interpolation methods. So from that, so once we've interpolated the entire surface, then we can calculate what our true residual is. And when I mean by you can see the true is in quote, that's subtracting the interpolated surface from the original surface. And that is also being represented as a percentage of depth, as you will see in the result soon. So from that stage, the next thing is maybe what really concerns us is, so how do we use the iBLUE estimators to estimate the uncertainty? And this is being done from the mainline data set, which is the seafloor that we've sampled. And of course, the final stage is to evaluate the performance and determine which of these two methods is the best estimator. So just to kind of give you a demonstration of how this workflow is going to work, because I know I've kind of said a lot, but I hope maybe this demonstration will help me drive home the point. So we have the complete coverage data set. Then we subsample that using, here in this case, we are using 128 meters line spacing. From that sampled surface, we interpolate that sampled surface to have a continuous surface, and we can calculate what the true residual is, which is the interpolation error, by comparing the complete coverage and the interpolated surface. And so what our interest is the true residual. Can we predict it? Can we predict what the interpolation error is? And then I think that's also what I kind of put down there. Can we use the sampled seafloor statistics to estimate the true residual? And I think I also need to be clear here, because as we see the result, the residual that you see as we go forward is the true residual, and what I call the uncertainty, those are our attempts in trying to estimate the true residual. So the uncertainty is estimated, and the true residual is the interpolation error. And of course, the way we evaluate the method is using a metric that we call the pass coverage. And what this measures is how successfully have we bounded the interpolation error. So, and hopefully with math, let me kind of just go forward. So what that is doing is it compares the estimated uncertainty to the true residual, and see if the estimated uncertainty is greater than or equals to the true residual, because we don't want to underestimate the true residual, because that would be bad. But slight overestimation is okay, as far as it's also not too much. So that is what the pass coverage is doing. And instead of just estimating the pass coverage for the entire area, we also try to see what the variability in that pass coverage is by partitioning the entire surface into spatial blocks using spatial bootstrap approach. Like that's not something I want to go. I really want to delve into, but I just want to tell, because as we see the result, we'll see the main pass coverage, and I will also see the uncertainty on that. So, and that's what I'm kind of like explaining on the slide here. So we partition the entire surface into n spatial blocks. Then we calculate the pass percentage for each spatial block. Then that would allow us to have like n bootstrap distribution of the pass percentages. And from there, we can calculate what the main pass coverage is and what's the confidence on those pass coverage values that we have. And finally, for us to select the best estimator, we are using a two-step approach. The first step is using a safety filter, and what that really means is we eliminate like any estimator that the main pass coverage is less than 90%. So it means like, because like we want something that is reliable, that will be safe for safety of navigation. So once the estimator is not able to, it's underestimating, that's what this is trying to say, then it does not get to the next stage. And the next stage is using statistical metrics to then now compare them, like in terms of root mean squared error and bias, and what is the severity of underestimation, and also like, we are also penalizing overestimation. So as much as we don't want to underestimate, we also don't want to overestimate. So kind of finding that balance is important. So those are the 4 metrics that we are using, and kind of like trying to combine those. We combine those into a composite score, into a weighted composite score, like which I'm not going to be going into the details of that. But what that allows us to do is, instead of comparing the root mean squared error for for the 2 methods, compare the bias, and it's easier if we can combine the metric into just one score. That would help us to say, okay, like this is the best method. We can kind of, without you looking into like each method and looking at the values one by one. So that's what that composite score will help us to do. So kind of like, talked about like all the methods. Let's look at some of the results, which I think may be the interesting part. So the first bed, which is the flat surface that I kind of like showed us earlier. So these are the set of line spacings that we considered. But in the interest of time, I'm just going to walk you through one of them, which is the 128 meters line spacing, and I'm going to summarize the result for the other line spacings, like in the end. So again, like I think we saw this earlier. We have the complete coverage. We sample it from the sampled surface. We interpolate that. Then we can get our true residual, and the true residual is what we are trying, is our target, is what we are trying to predict. So using like the methods, like so here we have the PSD iBLUE and we have the star iBLUE. So this PSD iBLUE is the spectral method, and the spatial stat method is SAI, and this is just the main. So this is not the envelope. So this, because like that was designed for the flat seafloor. You can see you can see like the pattern there, like maybe you can't really see closely, but the pattern is the same thing. But if we really subtract, if we take a difference between, let's go back one step, between the true residual and the PSD blue, and take the difference between the true residual and the star iBLUE, and try to see one way, try to see like how we've done. You can see like mostly everything is about here, which is this green, kind of like zero, but we have some funny patterns going on here, also here too, and that is as a result of like some artifacts in the original data set that were used. So this is not from the estimation itself, but it was kind of like inherited from the original surface that was used, which like I think brings up an important point, that the quality of the original data set is also important. Like, despite the fact that it has met like the IHO specification, but of course the fact that those artifacts are still on that surface is still transferred through our interpolation process and how we estimate our uncertainty. which I think it's interesting. So now looking at the past coverage, which is really the metric that we are trying to use. If we look at the two methods, which is the PSD here and SAR here, looking at them, the PSD has the past coverage of about like 95%, and SAR has a past coverage of about 93% or 94% thereabout, like which is good, and it means that these two, they pass the first phase of our filtering, which is kind of like eliminating either of the method that is less than the 90% pass coverage. So now the composite score is now going to be the judge now by kind of like looking at like the stats and looking at underestimation and underestimation and overestimation. And when we look at that, the PSD, which is the spectral method, like kind of like wins. Maybe that's not maybe you don't appreciate that enough. So let's look at this cost track, their cost track profile here. The residual in blue, that's our truth, like what we are trying to, our target. And this is how the method, the estimators have bounded the residual. So we can see PSD there in orange, and we see the SAR there in green. And it's they found the interpolation error like quite well. But does that mean that there are some times that they are not able to get it? They get it wrong too. Yeah, like there are some times here, and as you can see here, that none of them is able to estimate the uncertainty. But that's just one of the points. And the fact that the past coverage that we saw was 95% too, means that kind of tells us this earlier, that there are some times that we won't be able to bound the uncertainty, which is okay. I think with any system, there are some times that there's nothing that you can just do. So this is another example also showing the profile and how the estimators have bounded the interpolation error. In the interest of time, so this figure, this table that we are seeing here, help us to summarize what the best estimator across the spacings, because I told us that the spacing that the one I showed you was for 128 meters, but all the other line spacing that we tested, so we can see the mean pass coverage there ranging from about 91% to 99%, and of course we see what the bound on that is. And if we look at what the method that kind of dominates on this, that performs the best on this test bed, that's the spectral method, which is the PSD iBLUE. So now let's get into the more complex test bed tool, which is going to really test the limit of the estimators, because the flat is kind of relatively maybe simple, but in complex test bed, that's when you see how you've really done. Again here too, I'm just going to walk us through one example, which is going to be 256 meters line spacing, and we'll summarize at the end too. So again, same deal, complete coverage. We sample at 256 meters. We interpolate that. We get what our true residual is, which is our interpolation error. Then we want to estimate that, and this is what our estimates look like. So the one in the middle there is the PSD, which is the spectral method, and the one on the far right is the SAR method. Now this is the spatial envelope range. So that's the mean plus 1 times the standard deviation, kind of different from what we compared on the flat seabed. I think those are important notes that we should keep at the back of our mind. So we can see the pattern on the three surfaces, it's kind of they look similar, but when we look at the different surface, I think that will help us see how we are really doing. And again, the zero there is where there is no error, we've really interpolated, we've really estimated the uncertainty well. And yeah, you can see on this in the west, the northwestern part of the surface, you can see that there are sometimes we overestimate the uncertainty, which is good, and that's why as you are seeing them in blue, which is good for a complex surface. But if we look at the past coverage, which may kind of like maybe help us give us a number, like how well we've done for the spectral envelope range, like that, the past coverage is about like 92%, and when we look at the PSD, the spectral method here, like that does not even get to the past threshold that we said. So it gets to about like 88%. So like the spectral envelope range kind of like automatically becomes winner without even going like using the composite score to select the best method. But I think it's still maybe interesting to look at the two of them together in terms of like taking a profile across just a profile across the surface and trying to see how the estimators, how they bounded the interpolation uncertainty. And again, like you see sometimes that none of the method is also able to estimate bound the interpolation error. And again, if you look at what is going on here, like that's very complex. So which I think it's okay, like as far as most of the time we get it, we are able to estimate the uncertainty. That's good. But if the pass coverage is maybe less than 90, I think that's not good. So like that's something like to be careful about. Again, this is just another example looking at how the estimators have bounded the interpolation error. And sometimes too, like this is even quite good. Like most of it's kind of like bounded. I intentionally showed us the bad one first, but in this case, it's kind of like this profile kind of like, and again, it's because that's happening here compared to like when we were looking at something that the one that was here. So that's what the profile looks like. Summarizing everything in terms of like all the line spacings, the main pass coverage from like from the line spacing that we looked at here was from 80 meters to almost 1 kilometers, and we see the main pass coverage here, and of course like the best estimator here is the spectral envelope range, and we see that kind of like ranges from about 91% pass coverage to 95% pass coverage, and of course like that becomes the winner. So I think this figure helps to maybe so it helps to summarize the whole thing in a nice way by looking at the line. So what we have on the x-axis is the line spacing and the seabed type on the y-axis. So for flats, you see like the kind of like the purple color PSD kind of like dominated all through, and the complex surface, you see the spatial envelope range also dominated all through. So what are the takeaways like from like this like what like I mean what's the take home what are the points to take home? The first is like the way we've done this is iBLUE models interpolation error as a stochastic process, like using local seafloor statistics. That's the first thing. Then the interpolation error is being bounded like as we saw, like from about 90% to 95% of the locations. And the performance is being controlled by seafloor morphology, which I think we all know that, but like this is also kind of like, and again, this is something I also saw like doing my master's, like the seafloor morphology. It's very important in how we interpolate and how we set our line spacing. And the spatial envelope range was the best for like the complex terrain that we looked at here, and the PSD iBLUE is like it was the best for flat terrain, but that does not mean that the spatial average range didn't work, but like the PSD iBLUE performed better than it when we look at it from statistical aspect. Then iBLUE is kind of data-driven and computationally efficient compared to the classical quigging approach. And of course, this framework is still evolving and is extensible. So with that, I would summarize. And I think my first point is interpolation is essential for creating digital bathymetric model, but the uncertainty it's introduced must be quantified. And reliable interpolation uncertainty enables us to propagate interpolation error into the bathymetric products. It will help us to improve chart accuracy and safety of navigation. And of course, it will help us to optimize hydrographic survey designs, and it will give users greater confidence in the bathymetric products, for scientific application. And iBLUE provides us a practical data-driven solution for estimating interpolation uncertainty. Before I take questions, I would just like to thank all the support that I've received, during the course of this work. This work is being done in collaboration with the NOAA National Bathymetric Source team. And of course, I would like to thank the center, for all the support. And I know, and of course, NOAA again for the grant, which is supporting my work, and my advisors, for their continued support and guidance. And thank you, everyone, for coming and I would like to take questions now.
Now a few minutes for the questions, so please raise your hand and ask.
Larry.
Yeah, so very, very nice, Elias. How do you decide the kernel size?
It's based on the interpolation distance. It's a function of the interpolation distance.
So it's basically depends on the data set you got.
Yes. It depended on the data set that you get and how far the point you are trying to estimate its uncertainty, how far is it from the known point that you have. So this is data-driven. You use your sampled data, this data that you've sampled, the statistics is coming from there, and the kernel, just like you said, is a function of the distance that you are trying to estimate the uncertainty. Imam, you had a question?
If you could go back to your slides where you have all the.
No, sorry.
You have different spacing.
Oh, the spacing?
Right.
This one?
Yeah. Which of these spacings are we most interested in, given that continental shelves extend up to about 200 meters?
Oh, yeah, that's a good question. I think the spacing, as an hydrographer, the spacing is usually dependent on the depth that you are in. So for the depths that I've considered here, I've the way I selected the line spacings went from 2 to 6 times the average depth. So that's gave me that range. And intentionally, I also bumped it up, that's how I had the 512 and 1024, trying to push the limit and see how the estimators will do. So
my question is, are we mostly interested in the interpolation for deeper waters or for shallow waters? Oh,
well, yeah. I think we are more interested in interpolation for shallow waters because that is most difficult to survey. As you know, your footprint is going to be small, your SWOT rather, it's going to be small compared to in deeper water. So, and that's why if you look at the first slide that I showed for US waters, most of where we have the sampled data set, those setline spacing survey, it's really in the shallow water because that would take a ton of time to do full coverage data sets. And the shallow water is also important for maritime navigation. So which is more reason why we need to find a good way to do this. Because it's happening in shallow water, then uncertainty in shallow water is also important. But in deeper water, of course we care, but it's not as in shallow water. It's
That's very good presentation. I'd be very interested. You mentioned previous methods and previous research that had been done. Would it be worthwhile for you to take those same two areas and use those previous methods to see how much better iBLUE is?
Yeah, that's a very good idea. It's in pipeline. That's something that I plan to do. Like the previous method and even the classical quigging, try to compare this and see how we do. Those previous methods are even.
This would be a very good metric.
I totally agree. That's something that I have in pipeline to do. I've not just had the time to do that, but yeah, it will be done.
Just curious, do you need to formulate, or have you thought about ways of different interpolations to test on? Because you were doing a very regular thing. I mean, with all the interpolations in Blue Topo, it's very messy. So how would that affect things?
Oh yeah, that's a good point. With everything, you start simple and you you make it complex. So currently, this has been kind of like this. The algorithm is being used by the NOIR team that I'm kind of collaborating with to kind of how they're going to be using this for the National Bathymetric Source Project by looking at surveys that are not as simple as I did kind of regular when you have everything kind of scattered and of course as mariners, we know we don't navigate on a straight line, you have all this, so when you have all of those problems, how would that affect the results? But I'm trying to kind of focus on getting everything work, get it to work first before we start to kind of test that. But it's good that the National Bathymetric Source team, they're kind of doing that on the side, which I think I'm very appreciative of, because that will help us to test this usability of this approach. Right.
Nice. I can save you some time on Pete's question. Don't worry about trying to do any standard kriging, even universal kriging. It won't work. I've done it already. The previous methods would be an interesting comparison point, particularly the one from the 2006 paper, which is on the New Jersey shelf, which is a really interesting data set. There's a couple of, I have many questions we should probably talk about offline.
Yeah, I know.
I have a couple of methodological questions for you. So you're assuming that you're starting with a gridded product and then you subsample it. Now for testing, I understand that piece. Is it fundamental that you have to start with something that's gridded?
That is gridded? Well, I mean, nothing it is. It does not have to be gridded. It could be batty points.
So if you're willing to start with bathy points, then how do you deal with non-uniformity of your data in your method?
Oh yeah, that's a good point. So for the spacing, right, kind of the regular spacing of that. One way we are kind of thinking of is to resample the data set that you have, so that you make it regular. The other way is there is this way of calculating the power spectral density but that will not be using FFT. So that's calculating power spectral density of non-equally spaced data set. So that's something that's kind of just like you asked now, I know it's a tendency okay, when you have all this data set, but based on the way we are testing it now, which is something that's going to come up from the Blue Topo, from the National Bathymetric data set, is they won't be regularly spaced. So if we are able to resample and we are able to resample, just like I said, make it equally spaced. In fact, this equally sampled space is going to be, which will only affect the spectral method. It's not going to affect the spatial statistical method, which I think it's a very good winning point for this spatial statistical method. If you remember, all of this started by spectral method is what we wanted to use, but as we kind of enter the problem, we're okay, maybe we could also look for something else. So the spatial stats method is going to it will help to ameliorate that problem of because it does not need to be equally spaced, but for PSD it's going to affect it. the way to that is to use power spectral density of non-equally spaced data set, if I answered your question.
I think it actually may get you both ways. So if you have something that's non-uniform, then you need a more complex technique. There's actually a non-uniform Fourier transform you could choose.
Yeah.
But if you don't, if you have a regularly sampled one because it's gridded, then that gridding process has its own point spread function, which is modifying the spectrum.
Yeah.
It's going to cause you problems as well that you have to compensate for.
Yeah.
Although I think you might get better result with your power spectral method if you have mixed data where you have some that's high density and some that's low density, which is quite common because you have like a high density chunk and then sparser data next to it.
Yeah.
You could use the spectral component from the denser chunk and then go elsewhere. The other question though, and it's kind of a more fundamental question, is in hydrography, the tails of the distribution are often much more interesting and important than the mean. When you're looking at something like this, what you're telling me here is that something on the order of 7% of your area is not being covered by your test. That 7% is the tails of your distribution, as you can see from your diagrams where you showed the uncertainty envelopes that you were predicting. Those tails of the distribution, hydrographically, are really important because those are things that stand proud of the seafloor into which ships might bump. So when you do something like this, what you're doing is providing a product that has a sense of completeness and a sense of scientific rigor because it has an uncertainty, right? And that's a good thing.
Yeah.
But at the same time, you run the risk of suggesting an overconfidence in our ability to predict uncertainty, which might come back to bite us because the bits that we can't predict are really, really important. So what do you think of that as a problem? How are you approaching it?
Well, I think that's a very good point. I think one of the figures would help to really drive home your point. So the point where we are not able to, for instance, we are not able to estimate the uncertainty. I mean, from what we see here, it's not really the lower end of the distribution, just like you said, unless maybe I don't really understand what you are saying.
Well, see, if you took your residuals there, if you generated a statistical distribution of your residuals, it would have a peak at the low end, mode at the low end, and a very fat tail that would go up to about 35% of depth. Right? The values represented by that tail are things which are significantly different from the background bathymetry. Well, the problem is you didn't see it in your initial survey. You're still trying to predict that it's there, but your initial survey doesn't tell you that it's there. So anything you derive from it isn't going to predict that anomaly. It's anomalous. So, but when you generate a product that has a nice smooth surface and a good predictive uncertainty, anybody interpreting that does not in their head have the warning that things I didn't see might be missing from this result. It's like imagining you have two lines and a rock in the middle that you didn't see. Any prediction you're going to make linearly is not going to predict that, but it will predict an uncertainty that doesn't include that variation.
Yeah, I agree, and I think you got that feature detection part. I think it's something that we are not accounting for here. Which, we have to kind of start the problem somehow, and of course increase the complexity, just like I was saying. But usually, especially, for example, the skunk-striping, if we have we use those methods and we have the feature detection capability from SciScan, that would help solve that problem in a very nice way. But trying to detect the feature where you are interpolating, I think that's a very real hard problem to solve, and of course it's one of the limitations of even we interpolating in the first place, because the ideal thing is go to the field survey everywhere, but we've got to do something. So yeah, I think it would be kind of interesting to kind of talk more about this, like, with you, like, so.
Like I said, there's lots we could talk about.
Yeah.
And I think that's one that's really fundamental, because giving a false sense of security like this
Yeah.
is dangerous. And so that's something that I think we all of us have to be really cognizant of when we do predictions like this.
Yeah, I totally agree with you. Thank you.
Okay, we are at time. Thank you for being here. Another round of applause for speaker.